450 and 9. Okay. Now let's take a look at how we can narrow it down there. And so we want 5.84. So here we're going 45 to 94. So 45, 55, 65, 75, 85, 94. So maybe 5, 4/5, 8/10 of the way. What do you think? 8/10 of the way? Because if we think about this, okay, let's go. We're going to call this 95, and so we're going from 45 to 95. So we'll go 45, 55, 65, 75, 85, 95. That's 5. And then we'll go 4/5. 4/5 would be 8/10. 8/10 of the way. We'll just add another 8 here. And so I'd say 0.32988. What do you think? Yeah? All right, so let's try 0.32988. See what we get. No. .841 times 10 to the 5th. Okay, now this is close enough. We're not going to go for 5.840 here because 1, as long as it rounds to 5.84, we're fine because of the sig figs. And 2, we're starting to get a lot of decimal places here, and a lot more than we're allowed, but it's okay. And so we're done here. Looks like it's 0.32988. Which would be the best for our X value. And so if we go back to the nitrogen, the nitrogen was, we saw it's 1.0 minus X bar. And so to calculate the nitrogen at equilibrium, we started off at 1.0 bar, and we have minus X bar. And so we can figure it out. 1.0 minus X, X is going to be 0.32988. 0.32988. And so let's add some more zeros here. And then go ahead and do the subtraction. It's 2, 1, 0, 9 from 7, 6. So I get 0.67012 bar at equilibrium. All right, and so I see, well, that's not, what was my limiting reagent here? Was it the hydrogen or the nitrogen? Hydrogen. The hydrogen was my limiting reagent. So let's go back to the limiting reagent. It's 1.0 bar minus 3x. That's going to give me 1.0 minus 3x bar at equilibrium. And so this is 1.0 minus 3. What is 3 times x? And so that's going to be 3 times 0.32988. At 0.9896. 0.98964. Add some more zeros here. Give me 6, 3, 0, 1, 0, 0. 0.01036 bar. And then the ammonia, we started off with 0 bar, and then we got plus 2x, and so we have 2x bar at equilibrium. 2x would just be double 0.32988. So 0.65976. 0.65976 bar. And so what's going to happen is this: the reaction's going to proceed. Now, did I consume all my limiting reagent? No. If delta G were bigger, like more negative, and K were bigger, yeah, we could have consumed practically all, but no, we're going to have it left over. And this is what happens in a Chem 1B reaction. You know, the driving force isn't enough to force a 100% reaction. And so we have incomplete reaction. But the reaction is going to stop here because we've reached K. Once we reach K, the equilibrium ratio, then it's done. There's no more change. And so what we're going to see is, well, how much reaction did we have? We didn't have 100%. We had less than 100%. And so what we do is we base it. I mean, if we were to base it on nitrogen, let's call this 100. You know, then it looks like 32 or 33. If we base it on nitrogen, 32.988% reacted, or about 33% reacted. If we base it on hydrogen, how much reacted? Well, if this is 100, then it would be 98.9. Can you guys see that right on? So we had 98.9% reaction. 98.9%. That's because my initials is 1. 9 sub 6. So about 99% reaction. I should be happy with that. You know, 99% reaction. But can we do better than 99% reaction? You know? Let's say I wasn't happy with 99% reaction. Is it possible to get more reaction out of this? It turns out it is possible to change the driving force. You know, it is possible to make the driving force even more favorable. If I make the driving force even more favorable, like if I change delta G naught, I can make it more favorable, which will change my ratio at equilibrium here, the K. And so, yeah, it is possible to do that, to change my final ratio. And so what I'm going to do is, let's say I'm not happy with 99% reaction. Let's say I want more. Let's say I want like 99.99% reaction. And so what I'm going to do is I'm going to see, you know, is it possible? Is it possible to get 99.999% reaction? I want 5 nines, 99.999% reaction. Well, in order to get 99.999% reaction, I have to have a bigger delta, you know, bigger driving force with the delta G, a more negative one, and that's going to make K bigger. Right? In fact, to get 99.999% reaction, I need the reaction to proceed and then stop. Once it hits 99.999%, I'm going to tell the reaction to stop. Is it possible to tell the reaction to stop at 99.999%? Well, it is if that's the final ratio. You know, if the final ratio is 99.999% reaction, then the reaction is normally going to stop there. You know, the reaction normally stops here. It stops at 98.96% reaction. We can't do anything else because this is as far as it's going to go. And so what we want to do here is this. If we get this, if we have 99.999% reaction, then what is the K value that would be associated with that? You know, that K value is where we have to stop. And so for 99.999% reaction, what must be the K value? And then see, you know, is that possible to get that kind of K value or not? And it turns out, you know, K depends on temperature, just like delta G depends on temperature. In fact, K and delta G are related. And so what we're going to do is we're going to first figure out where we want the reaction to stop. And so initially I have 1.0 bar, 1.0 bar, and then 0 bar. And if I have 99.999% reaction, then I gotta lose 99.999% of our limiting reagent. What is our limiting reagent here? Limiting reagent is hydrogen, so I need to lose 99.999. In other words, I need to lose 0.99999 bar worth of that. That would be 99.999% of 1. Okay, then I wanted to stop there. Stop there such that I lost that, so I'm going to end up with 0.00001 bar remaining. I have 0.001%. This would be 0.001% if I move the decimal to make it a percentage. 0.001% left, unreacted. Now, what I need to do is I need to make sure the reaction stops here and doesn't proceed any farther. I can do that, you know, if I can get the K, you know, this ratio, the desired ratio some way by either manipulating temperature or something else. And the way we're going to do it is by manipulating temperature. But the thing is this. I call this minus 2y. The reason I call it minus 2y is because y is a known. If that's 3y, sorry. I call this minus 3y because y is known. I could easily figure it out. If this is 3y, then y must be, yep, 0.33333. And so here, what I'm going to get is this. I'm going to lose, over here I'll lose y. And so that's 0.3333353. And over here I'm going to gain plus 2y. Well, plus 2y is going to be double y, which is going to be 0.66666, 5 sixes. Okay, so that means that at the end of this reaction, I need to consume 33% of my nitrogen, and I'll be left with 66%. And so we'll have 0.5 sixes, I think, and a 7. Be 4 sixes and a 7, sorry. 4 sixes and a 7 bar. And then over here I'll have 5 sixes. All right, so if this was the change, then this would be 99.999% reaction. And the K value would be the product to reactant ratio, so it'd be 0.66666 squared divided by 0.66667 divided by 0.4 zeros and 1, quadruple 0, 1 cubed. And so what is the K for this? if I could get a K value this, is this right? The calculation?
I got that.
You got that? If I could get this K value, then what's going to happen is the reaction is going to proceed until I hit this ratio. Once I hit this ratio, then we call that the end of the reaction, equilibrium. And so that way I can get 99.999% reaction. Now, can I get that K value? And so we got to see, you know, what does K depend on? Sure, I can get that K value, you know, because I've seen it before. I've seen this, that the delta G naught is equal to minus RT ln of K. And so I just plug in, I have my K, I have my delta G, I just solve for T. And so the temperature is equal to E to the minus delta G naught over RT, which is equal to, well, delta G naught is the, this will be a minus 32.90 kilojoules. So let's convert that into joules. So 32,900 joules divided by 8.3145 joules per Kelvin times 298 Kelvin.
Are you trying to find T or K?
Oops. I'm trying to find T.
Yes.
Sorry, this is wrong. T is even easier. T is equal to delta G minus delta G naught over R ln of K. Oops. So this is going to be a minus 32,900 joules divided by 8.3145 joules per Kelvin, natural log of K, which is that 6.666 times 6665 times 10 to the 14. So I have the K still in my calculator. I'll just take the natural log of that. Answer. Oops, I had it. Come on. These keys are, oh, there it goes. Oh, the answer. Does somebody have it? Actually, I don't see this. There's a bird. 115.9 Kelvin. Somebody have it? Did they get this? 115? 115.9 Kelvin. I'm not, you know, Kelvin doesn't come up, so 115.9 Kelvin minus 273 is minus 157.1 degrees C. $157.1. Okay, are we good? Just Kelvin minus 273. Is that right? I just converted it. Yeah. 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 Does this look good to you? No, this looks bad. Unfortunately, this is wrong. This is all wrong, but I see this all the time. Like I said, you know, it's all wrong. It kind of looks good, you know. See, my battery's dead. Everything looks okay, it seems to. Everything seems to look, I have my delta G, I have my R, and I have my K. Everything looks good, but it isn't good. It's bad. Why? Huh? It's because of delta G naught. Delta G naught is the problem here. I need the delta G naught at temperature T, but I'm using the delta G naught at temperature 298 Kelvin, and this temperature is wrong anyway. This is all wrong. Unfortunately, that's wrong. So what I have to do is I have to look at the relationship between delta G, K, and T. So maybe there's another way we can figure it out. And so I go back through the thermal equations and I see, oh yeah, we have this equation. Delta G is equal to delta G naught plus RT ln of Q. Okay, this is going to be at temperature T, and this should be delta G naught at temperature T. And so at equilibrium, that's what we want. We want to set this equal to 0. If we set this to 0, then we're at equilibrium, which means Q is going to be equal to K. And so we still have trouble here because we don't know what delta G naught at that temperature is. However, we do know this. We do know that delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. And so that would be my delta G naught at temperature T. This is going to be plus RT ln of K is equal to 0. All right, and then we can say that, well, delta H naught at temperature T is about the same as delta H naught at 298 Kelvin. That's a reasonable assumption. Minus T delta S naught at 298 Kelvin plus RT ln of K. And then we're going to solve this for T. This is equal to 0. If we solve this equation for T, then let's factor out T out of here. And so we're going to get delta H naught at 298. Let's factor out a minus T. Okay. Let's just factor out a T. Plus T times delta S naught at 298 plus R ln of K is equal to 0. And then solving this for T, we'll just maybe subtract this from both sides or do something like that. And so we'll get T is equal to delta H naught. Actually, I'll leave this on this side and take this away. So we'll end up with delta S naught minus R ln of K. And this will be K at temperature T. K at temperature. K depends on temperature as well. So K at temperature. Now it works out, right? Because we know what the K value is, we just don't know what the temperature is. And so here, I don't know what the temperature is, but this is the desired K value. This is the number that we want. And so what we do is we can figure out what the temperature is going to be by plugging in our delta H, delta S, and ln of K. And then we can get it. Let's see. Just because we calculate the temperature, now this is the correct equation, and it still could give us the wrong answer because it might give us an impossible temperature. We might not be able to achieve that temperature. So let's say we calculate the temperature comes out to minus 150 Kelvin. Minus 150 Kelvin is not possible physically, so it didn't work out. sometimes it's a calculation error, sometimes the equation is correct, it just doesn't give us the right number. Did we calculate our delta H and delta S last time? No? We can get those from the book. And so this is the equation that we're going to use. And so, you know, for a given t, and this is what we did, you know, we didn't just want delta G equal to 0. Generally, when we get our delta G equal to 0, we're going from spontaneous to non-spontaneous, or non-spontaneous to spontaneous. You know, delta G is changing sign, going from positive to negative, or negative to positive. It has to pass through 0. So one of the targets is 0, getting a delta G of 0. Well, in this case, it's already spontaneous. If we set delta G equal to 0, then we're going to go from spontaneous to non-spontaneous. There's no point in doing that. And so delta G was already negative. That's happy. We didn't have to mess with it. The only reason we mess with it is to get a higher yield of product. And so we said, okay, we want 99, we want higher percent reaction. And so this is it. So rather than targeting delta G equals 0, like in this case, it wouldn't make any sense to target delta G equal to 0 because, again, if we did that, then we're trying to make it non-spontaneous. We don't want to make this non-spontaneous. So instead of targeting a delta G equal to 0, what we're doing is we're getting a K value, and we're going to target that K value. This is the desired K value to give us that percentage of reaction. For this K value, well, K depends on temperature. You can see it here. And so whatever K value we have here, we can figure out what the temperature is.
So if we ever got like T equals negative 150 Kelvin,
right. Okay, if T comes out to negative 150 Kelvin, then what we conclude is it's impossible. It's impossible to get that K value. And for some reactions, we can't have any K value we want. You know, the K values are going to be within a certain range because they're certain temperatures. So if somebody said, you know, I want some ice. I want some ice at 400 degrees Celsius. Are you going to give them some ice? They want a hot piece of ice at 400 degrees Celsius. Can you give that to them? They say, well, why not? Because can you heat up the ice? Yeah, but you know, it seems like you can just keep heating it up, but you know, there can be physical things that are going to prevent you from. And so the same thing happens here. If you get a temperature that's nonsensical, minus 150 Kelvin, then it's not possible to get that K value. You have to reevaluate it and go back and say, okay, what is possible? You might not get 99.999%. You might get 63% reaction. You know, but that's as high as you can get. Now, we like to see, you know, what we think is possible is to think, okay, I have a furnace. How hot did a furnace get? You know, well, my furnace might get up to 200 degrees C, 300 degrees C. I used to work with a special furnace, and it was an electric furnace. This electric furnace got to 1600 degrees C. 1600 degrees C is extremely hot. The furnace was made out of platinum metal, because platinum has a very high melting point, 1600. So you need it just melting, almost melting. That furnace used to sit on our lab bench, and it consisted of pounds of platinum inside there. This was when platinum was much cheaper. The furnace was still expensive, but now that furnace, you can't even buy it probably, it's so expensive. But so sometimes we're kind of curious, you know, we're going to be limited to the range of temperatures. How cold can you get? You know, how warm can you get in your laboratory? And so sometimes we're just interested in what, you know, impact temperature has on the K values themselves. So we can see it here. That's solving for temperature. If we want to see, you know, how K is impacted by temperature, then can we use this? You know, if we did K is equal to E to the minus delta G naught over RT, we're really restricting our temperature here. This would be K at temperature T, delta G naught at temperature T, RT. But sometimes what we do is we just leave it in this form, the natural log of K. The natural log of K at temperature T, that would equal minus delta G naught over RT, like that. And so what we can do here is we can do this, except the problem is delta G naught depends on temperature. So to make it clear what's happening here is we can change delta G naught into delta H naught at temperature T minus T delta S naught at temperature T over RT. And then what we can say is this, well, delta H and delta S don't change much with temperature, so we're just going to get a minus, parentheses, delta H at 298, understand, minus T delta S at 298 over RT. And then we can separate this, so what we'll get is something like this. We'll get minus, in fact, I'm going to rearrange this a little bit. We're going to get minus delta H naught over R times 1 over T. And then we'll get this one here. It's just divide that here. We're just going to get a plus delta S naught at 298 over R. All right, and so here, do you see this is kind of this y equals mx plus b type deal where x is 1 over t, y is ln of k. So what we can see is we can see how ln of k varies with temperature and graph that out. So this should be linear, a linear relationship. And we'll see, what range ln of k's have. If we have ln of k's, we're going to have to convert that back to k's by taking the anti-log, but that's not a big deal. And so typically what we'll do is graph this out, see what the trend is. Another thing that's done to compare how K changes with temperature is this. This is a common trick in science, and that is we'll take ln of K at temperature 2, so I'll just call it K sub 2, minus ln of K at temperature 1. And so ln of K at temperature 2 would be equal to minus delta H 298 over R 1 over T 2, temperature 2, plus delta S naught 298 over R. Okay, so this would be ln of K2 here. And then we'll subtract ln of K1. ln of K1 would be minus delta H naught 298 over R 1 over T1 plus delta S naught 298 over R. We assume that the delta H's and delta S's at temperatures T2 and T1 are the same. Then we use the property of logs. ln of K2 minus ln of K1 is ln of K2 divided by K1. And this is going to equal, I'm going to simplify this a little bit. I'm going to factor out the delta H298 standard over R. And then we'll just say 1 over T2 minus 1 over T1. This is a very famous equation in thermal. This equation is this. If you're given K1 at T1, we can solve, or we can determine the equilibrium constant at any other temperature, T2. And so you just pick a temperature, T2. What we need to know is delta H for the reaction process. And so this is a very famous equation here. What is it called? Van Hoff?
Yeah.
Van Hoff equation? The Van Hoff equation. The Van Hoff equation gave rise to another very famous equation. You'll probably recognize this one. And so let's look at an example application for this Van Hoff equation. An example application for the Van Hoff equation looks like this. Let's just look at the vaporization. So if I take A, any substance A, which is liquid, and it goes to a gas, then I know what is Q in this case. Q is going to be the pressure of a gas. In other words, we call this the vapor pressure. And K, once we hit equilibrium, will be the equilibrium vapor pressure. Q is just whatever initial vapor pressure you have. But K will be the equilibrium vapor pressure of A, which is the liquid. And so if we just do that for this, we can generate this equation. Ln, okay, that's all K. The reactants are pure liquid here, so the pure liquid has an activity of 1. Right? Pure liquids have an activity of 1. And so it's just going to equal PA. And so I'll get that the vapor pressure at temperature 2 over the vapor pressure at temperature 1, we'll take the natural log of that, is equal to minus delta H. This is delta H of vaporization at 298 under standard conditions, divided by R, 1 over T2 minus 1 over T1. Sorry. Do you recognize this equation? If we take the Van Hoff equation and just use it for this vaporization process, we come up with this equation. Have you seen this one before? Yeah, you've seen this one. This is a chapter 12 equation. Do you recall the name of this equation? It's a very famous equation. Starts with a C. It's named after 2 people, actually. 2-person equation. Interestingly, both their last names begin with a C. Yeah, this is the Clausius-Clapeyron equation. And so if we just take our Van Hoff equation and just apply it just to vaporization of the liquid, then we get the Clausius-Clapeyron. The Clausius-Clapeyron equation allows us to calculate the vapor pressure at any temperature. And so, for example, what is the vapor pressure of water at 25 degrees C? I can calculate this equation. It's about 0.032 atmosphere. All right. Any questions relating to this? Now, we're going to continue with lab, but the lab's not going to take too much time. What I want you to do, though, is I'm going to do a little quiz. It's related to the lab, but this is going to be a low stress quiz because it's open books, open notes, and you can check with your neighbors or classmates. You can check your answers. This is kind of the peer review. You know, peer review is how you can check your answers. Check it by peer review. Hopefully, one of your peers knows the correct answer, but sometimes nobody knows the answer. And so this quiz is a reaction. We're going to take some potassium dichromate, some hydrochloric acid, and some ethanol. If I mix these together, I want you to predict the product, if any. Predict products, write the balanced net ionic equation, and then comment on the driving force. Big driving force, small driving force.
This is a one-step reaction.
This is a one-step reaction?
Yeah.
What do you mean by one-step?
Like sometimes like one reacts to other and then that lets something else react.
over and see is there any obvious reactions. But the first thing is just treat it as one step and just try to get that one step, because I'll tell you, nobody was able to get more steps. Well, just give it a shot and see. How much time do you think you'll need for this? 10 minutes? 10 minutes, 10 to 15 minutes was the time I allotted for this, but let's see. Let's do a progress check in about 10 minutes. So this is kind of a, you can work in groups. This is like a group quiz, not an individual quiz. Or it can be an individual. If you like working alone, that's fine too. But this one's going to be worth 5 points. You should make an effort to make sure your answer meets peer review. Science is peer review, basically. And just how we can check our work.